Hey guys, good morning. Welcome to the Aerospace Structures lecture series. Today we are going to see about bucklings of plates and aircraft load analysis. So, in introduction, we have normally sees buckling is a structure instability due to the compressive stress. Let us take the building columns, the pillars which takes the compressive load. Due to the structure instability, it will get a failure or produce the cracks the common in the slender components like columns and plates, the reason. Sudden lateral direction changes the shape and dimension occurs beyond the critical load. This compressive load makes the structure instability, which creates the buckling of the structure. It is not necessarily related to the material for this failure. The government design limits for many aerospace components in aircraft the landing gear and the wing structure and fuselage structure strongly affected by geometric and boundary condition. This is the things which affected in the design. To preventing this buckling is essential in aerospace structural safety and operation. So let us go with the structural plates which is located in fuselage of aircraft. Will usually would say the plates are flat 2D structural element with this the minimum thickness used in fuselage skins, wings, bulkhead, and etc. So we can be it can be a isotropic or anisotropic material like composites also we can used in the most of the aircraft fuselage and wings. Load in plane and out plane deformation may occur in plane like tension, compression, or shear. This will make the structural plates to failure. Whereas out of plane deformation, we usually call it as buckling. So buckling in plates is critical in thin-walled structures in fuselage and wings. These structural part analysis is a key in lightweight design of airplanes, aircraft, and other flying machines. Coming to the plate buckling, in the equations based on the equilibrium internal and external forces, the governed equation from the Kirchhoff love theory. The critical stress sigma CR equal to K pi square E by 12 1 minus gamma square into thickness by T by B the whole square, which is the purely depends upon the plate dimension like thickness and boundary condition, where K is the buckling coefficient of the loading. This can be analysis due numerically in using of finite element analysis, any like using any tools like ANSYS and Abacus and so on. Coming to the types of bucklings in the plates, due to the compression load in one direction, that will be called it as uniaxial buckling. Compressive stress in two directions, we can call it as biaxial buckling. Due to in-plane shear loads, that is shear buckling, occurs in thin elements in stiffness like local buckling and global buckling as a different. These are the behavior in different material, different geometry, and different support conditions under the different modes, which helps to understand how a better structural design to avoid these bucklings in the plates. Now coming to the plate boundary condition buckling behavior, in any edges and different conditions which influence in critical buckling stresses, like four supporting edges will fixed and two supported edges are fixed like simply supported beam clamped and free supports. This clamp range raises the buckling load capacity. In simply supported plate shows the buckling resistance. So in real world, aircraft structures have mixed edge conditions, which makes the aircraft design must account of actual support mechanism to increase the life and avoiding the buckling behavior. Now coming to the stiffened panel in the aircraft structures, increases the buckling resistance in thin plates, where we are adding the load bearing capacity by using of various cross section like I section, Z section, T section, in fuselage, wings, and control surface. It can be stringer, frames, ribs, or other structural elements to maintain the load bearing capacity, which also reduces the unsupported length and increases the rigidity, which plays the major optimality for the weight and the strength. Buckling modes may shift from panel to stiffness, which is the critical in composite structure during design phase. Coming to the buckling versus metal failure, in buckling is a geometry instability, not a material yielding. It's different. Metal can be interact even after the buckling also. It can also take some loads after it buckles. Post-buckling strength may exist in stiffened panel. Aerospace designs often tolerate limit load buckling cases. So yield will lead to plastic deformation, buckle to collapse. So this is the major consideration of buckling must be considered load analysis and made failure of the materials. So aircraft structure, loads and types. So generally in aircraft, the aerodynamic loads, inertia loads, ground loads, thermal loads, internal pressure loads, gust loads. These are all due to the existence of drag, lift, and moments flow over the external body of the aircraft. Due to the aircraft marks under the different velocity or acceleration. Ground load due to taxiing, landing, and brakes is due to this thermal due to temperature, pressure due to internal pressure, gust due to turbulence, and air effects, wings and tails. These are the few loads which will affect which will make the fatigue load. Structural to monitoring is needed to be controlled. The load path in aircraft structures, loads are transferred through skin frames and stinges. Wings from the skin, ribs, spars, and fuselage. In fuselage, the load will be in axle bending and hoop stress. So the load transfer affects the buckling and the fatigue life of the material, which can be interacted with the load factor and the load flight envelope. Load factor is defined as it's a ratio between lift to weight ratio, which will indicate how much lift can produce in the aircraft during various maneuvering points, which makes the aircraft to the limit of the maneuvering and typically range from 1g to plus 2.5 g. So positively till minus 1g and negatively 1 inverted to the plus 2.5 g in transport aircraft. Buckling must be avoided even the extreme condition so that the load from envelope used in the design and testing phase. Now coming to the load analysis method in aircraft, we have few methods: classical analytical method, finite element method, experimental testing, wind tunnel testing, and flight testing. So classical analytical method is the simplest shapes of deformation of the calculations we can do this method, whereas the FEM used for the complex geometry. Experimental tests for strain gauge and load cells are used to understand the loading analysis pattern. Internal tests to estimate the aerodynamic loads on different aerofoils, wings, and different fuselage configuration. Flight test is the validate the real world structural behavior of the aircraft. Now coming to the design criteria consideration to prevent buckling. This is one thing we have to understand how to prevent the buckling in an aircraft and other structures. Maintaining minimum thickness to provide local buckling so that it can avoid the large buckling. Use stiffener for long stringer structure. Also avoid sharp corners and discontinued faces to avoid the increasing of buckle. Choose metal with high elastic of modulus, which is having the high resistance, high stiffness, which will avoid the buckling. Optimum geometry to minimize the buckling zone. Apply load smoothly and symmetrically so that it can be not be unsymmetrical and which will avoid the buckling. Consider post-buckling behavior in weight sensitive design. Now coming to the buckling in composite aircraft panel, most of the aircraft nowadays they are using more than 50% of structural component using composite material, which is having the high strength to ratio. This is made up of fiber oriented, affect the buckling resistance. Delamination can reduce the stiffened panel stiffness. So sandwich panel shows different buckling modes. Due to this, the failure criteria are more complex than metals. So much consideration, both metal and geometric and non-linearity. This FA tool can essential to analyze the composite buckling of aircraft panels. Let us take one case and the incident. In 1950s, the earlier aircraft failed due to the inadequate buckling analysis. This is due to pressurization include buckling and fatigue. Modern aircraft are used to use extensively buckling simulations, bucklings of wing, skin, fuselage, and during the flutter in some fighter also taking place. Testing at Boeing and Airbus involves a large-scale mock-up or taken place in the company itself. So the military aircraft having a higher buckling tolerance so that it can be operated in very high structural load during the maneuvering. So learn from failure driven the innovation in the design of the aircraft. In conclusion, the buckling and load analysis. Buckling is a critical failure mode in the structure, thin structure. Aircraft planes must be designed to resist compressive load. So load analysis helps to understand the structural size and the layout. Safety margin ensures robustness in the extreme condition. Both analytical numerical tools are essential to understand the buckling behavior of the structural components. Composite structures needed in advanced buckling consideration in advanced aircraft as exam structure. Integration of design, simulation, and testing ensures the airworthiness. So here we are understanding the key components of buckling and the load analysis in various structures and aircraft structures. So we'll see in the next class. Thank you.